So I sent you into the other room to go work on these radical expressions and sketch these graphs. So if you sketch the graph of the square root of x, what you would get is you would get a graph that kind of looked like that. What is the domain of that graph? What are my possible x values? So think of it this way. What can't x be in this graph?
Less than 0.
Less than 0. So the domain is that x has to be greater than 0. And it can be any real number greater than 0. So that's the notation, the set notation. I could also do this as interval notation where I say it has to be from 0 up to infinity. So the square bracket goes on the 0 because it has to equal 0, and the curved bracket on infinity because, again, infinity is not so much a number as it is a concept. Because if you count up to infinity, I'm going to go infinity plus 1, and I'm going to beat you. So for what values of x is the radical expression defined? It's the same as the domain. It's defined for all the positive x values. So all the values of x that are greater than 0, this expression is defined, meaning I can find a value for y. If I look at the radical expression, the square root of x minus 2, where did that graph start at? 2. And kind of had the same similar shape as the graph above it. It just was shifted over 2 spots horizontally. What's the domain of this graph? What are all my possible x values? So again, think of it the other way. What can't x be? Less than 2. So it has to be all the values that are greater than or equal to 2. Which again, in interval notation, would be 2 to infinity. The restrictions. The restrictions are all the values that x can't be. So what can't x be?
Less than 2.
Okay, why can't it be anything less than 2? So in other words, what happens if x is equal to 1? Why doesn't it work in the equation? And what can't I do?
Square root.
I can't square root a negative. So if I said you had to do this algebraically, you had to find the restriction algebraically, what would you do to find it algebraically? Well, what do I know about everything underneath the radical sign? It has to be positive. That's the only way that I can take the square root. So what is underneath the radical sign has to be greater than 0. And now I can solve that equation. I add 2 to each side, and there's my x is greater than 2. So how to determine the restrictions algebraically? Let the expression under the radical sign be greater than 0 and solve. And then the last one was the square root of 3 minus 2x. So this time when I go to solve it, my radical actually flipped around and went the other way. And it started halfway or in between 1 and 2. Kind of went in that direction. So now we have an example where it is possible to have negative x values. So in this case, what are the restrictions? What can't x be? Anything greater than 1.5. So anything greater than 1.5. It can be equal to 1.5, so I don't have an equal sign underneath there. It just can't be greater than 1.5. So if I wanted to determine this algebraically, I would take what's under the radical sign and make that, say this has to be still greater than 0, because what's underneath the radical sign still needs to be positive. With this negative 2x, I'm going to choose to move it to the other side of the radical, or sorry, the other side of the inequality. And then that'll make it positive, and then I can divide by 2. And there's x has to be less than, and it can be greater than, or sorry, it can be equal to 0. So x can be less than or equal to 3/2. If I decided to solve this by moving the 3 over, and then I would divide by -2, so I'd still get my 3/2, but what I would need to remember is when I'm dividing by a negative value, I have to flip my inequality sign. And I still get the exact same inequality. X is less than or equal to 3/2. So these are all examples of radical equations, radical expressions, because they contain a radical symbol. The value of the variable that satisfies the equation is called the root of the equation. And we're going to look at solving radical equations both algebraically and graphically. So if we look at class example number 1, and we want to solve radical equations, what can I do to algebraically determine any restrictions? Let's read the question first. So to determine restrictions, I want to make sure that whatever value of x I put into this equation, my radical will always be positive. So to solve for these, I let the expression underneath the radical sign be greater than or equal to 0, and then I solve. Move the 1 over, it would become negative, and then I would divide by 4. I get -1/4. If I look at B, I have 2 minus 5x. The -7 is not underneath the radical sign, so it has nothing to do with my restrictions. My restrictions are simply what is underneath the radical sign. Sorry, guys, we're not actually done this one. My restrictions, these would be my possible values. So then my restriction, or no, sorry, I forgot this part. There we go. X can be anything that is greater than or equal to -1/4. So then with B, I take what's underneath the radical sign and I let it be greater than or equal to 0. If I have a negative variable, it's easiest to move it over to the other side and make it positive. And then divide by 5. And I get that x would have to be less than or equal to 2/5. And again, x would have to be a real number. In C, I have 2 radical expressions. So if I solve both of them, x minus 2 has to be greater than or equal to 0, which means x would be greater than or equal to 2. And x minus 4 has to be greater than or equal to 0. And x has to be greater than or equal to 4. Now take a look at the 2 restrictions. Can I have a number that's greater than 4 and greater than 2? Do all of the numbers fit that restriction, or just some of them? So let's think of 2. 2 works here. Does 2 work there? What happens if I put a 2 in for x? I get a negative. So does 2 work for this one? Or sorry, for this one? No. Does 3 work for this one? No. The only ones that work for that one is the 4. So this actually becomes my restriction, and this one I have to cancel out. So when you have 2 restrictions, you have to think of what restriction works for both equations in all circumstances. So if I look at D, I have x plus 2 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 2. And then 3 minus x greater than or equal to 0. Move the x to the other side. And I get that x has to be less than or equal to 3. So the other way that this can help, or that I can try to figure out when I have 2 restrictions what I can do to combine them, is I could graph this. If x has to be greater than negative 2, that's what it would look like. Then I have that x has to be less than 3. X being less than 3 looks like that. So the values that would satisfy both equations are the values that would be in between. So the way that I would write that is that x has to be less than or equal to 3, or it could be greater than or equal to negative 2. And it can be any values between negative 2 and positive 3. So I'm going to give you a moment, and I want you to try to do E on your own. So when I go to solve for each of these expressions, I get x has to be greater than 7/2, which I kind of converted to a decimal so that when I went to kind of look at a number line, I knew which fraction was bigger than the other. 24 minus 5x, move the 5x over to make it positive. Then I don't have to remember about flipping my inequality sign. Divide by 5, and I get 24/5, which is 4.8. So now when I go to put it on a number line, I know which one should be in which position. X has to be greater than 7/2. X has to be less than 24/5. So then when I go to combine this, x has to be less than or equal to 24/5, greater than or equal to 7/2. And x could be anything in between. So it's important to know what the restrictions are with a radical equation. Because when we get into algebraically solving radical equations, we need to check that our solution fits within the parameters. Because sometimes when we go to solve them, we do change what the equation looks like, and it could actually give us solutions that don't fall into it. But before we get into solving these algebraically, we're going to look at solving them graphically. So when we go to solve this graphically, consider the radical equation, the square root of x plus 1 equals 4. What values of x is the equation defined? So in other words, what are my restrictions on x? Well, x plus 1 has to be greater than or equal to, not 4, greater than or equal to 0. My radical always needs to be positive in order to solve it. So I move the 1 to the other side, and I get that x has to be greater than or equal to negative 1. So if I went to solve this algebraically and I got an answer of x equals negative 4, it's not greater than negative 1, which means it can't be a solution to the original equation. It might have been a solution to the equation I came up with through the process of solving, but it does not fit in the original equation. So now if I wanted to use a graphing calculator, how would I use a graphing calculator to solve this? So if I want to use the graphing calculator, what I would do is I'd go to my y equals. If you have any equations in your y equals, just clear them. I'm going to let y1 be equal to what's on the left side of my equation. That's my x plus 1. So the square root of x plus 1. Depending on your calculator, yours might do the square root or the radical symbol and open up a bracket. Then just close the bracket after the 1. And then I'm going to let y2 be equal to 4. The next thing that I'll do is, because there's a screen here for me to follow, I'm going to match my window settings with the screen. So I'm going to press window. If I look at my x's, the smallest x value that's shown to me is -3. The biggest x value shown to me is 20. So I'm going to go from -3 to 20, going up by ones. And then my y's went from -5 to +5. So what I want you to do is I want you to sketch that graph on the screen that's in your book. So now I've got this sketched onto my paper. To use the calculator to solve for the equation, what you want to do is you want to find out where do the two graphs meet, because that's the point that they have in common. So that's using the intersect feature. So I go second, calc, I choose number 5, which is intersect, and then it says first curve, which means if I'm on this curved part, try to move it a little bit closer to where the two graphs meet. Press enter, then it's going to jump up to the second curve and ask me to do the same thing. It's going to say guess. I don't want it to guess, I want it to calculate, so I press enter one more time. And then up comes the word intersection, and it says x equals 15 and y equals 4. So that's the point that both graphs have in common. That becomes my solution point. So that's this point right here, 15 and 4. So I let y1 be equal to x plus 1. I let y2 equal, or sorry, this should be the square root of x plus 1. y2 equal 4. And then I go intersection. So the solution to the equation would be that x equals 15. If I wanted to verify this algebraically, when we go to verify equations, we have our left side and we have our right side. We do not put an equal sign between them, we put a line, because what we're trying to do is show that the left side will equal the right side. So I substitute 15 in for x. What's 15 plus 1? And what is the square root of 16? So now I've shown that the two sides are equal. So what I want you to do is questions 4, B, and C. So in solving radical equations algebraically, the key is to get rid of the radical. So the inverse operation for square rooting is to square. So as long as I do the same thing to both sides of the equation, I'm okay. So if I square this side of the equation and I square that side of the equation, I have not changed the value of the equation, I've done the same thing. When I square the square root, they cancel each other out, and I'm left with x plus 1. And then I've got 4 squared is, subtract 1 on each side, and x would equal 15. The next thing that I want to do is I want to verify the solution. So if I go to verify the solution, I'm going to put 15 into the original equation. So when you do the verification, it's always in the original equation. We don't put the equal sign, we put a line, because what we're trying to show is that the left side will eventually equal the right-hand side. Square root of, 15 plus 1, 16, to which the square root is 4. Now, sometimes when we go to square both sides of the equation, we sometimes end up with a little bit more complex of a system. The other thing that can happen, and this is in investigation number 2, is we have 3 plus the square root of x minus 1 equals x. So when I go to solve this equation, what I want to do is I want to isolate the radical if I can. So I want this square root of x minus 1 to be by itself, so I subtract 3 on each side. Now that the radical's by itself, I can square both sides of the equation. So again, when I square the left-hand side, when I square the radical, I'm left with x minus 1. And with the x minus 3, when I go to square that, remember it's x minus 3 times itself twice. So if I use the distributive property, what I'll end up with is x squared minus 6x plus 9. X squared plus 9, typically students will get those two terms. It's the 6x in the middle that we forget about. So we have to remember that that negative 6x was from the negative 3x and the negative 3x. So now that I have my equation expanded, what I would do to solve it is I would move everything to one side of the equation. X squared's already positive, so I'm going to move the x and the negative 1 over, which will give me negative 7x and a positive 10, leaving me with 0. And then I'm back to solving a quadratic equation like we did earlier in lesson 5. Two numbers will multiply to 10 and add to negative 7.
Negative 2 to negative 5.
Yep. So what are my possible solutions? What could x equal?
2 and 5.
2 and 5. And then what I want to do in the last part is I need to verify the two solutions. So to verify the two solutions, I can start off with the 2 first. So I get the square root of 2 minus 1, or sorry, 3 plus the square root of 2 minus 1 equals 2. So I go back up to my original equation. What's 2 minus 1? 1. What's 3 plus 1? Does that work? Yes or no?
No.
No. So is x equal 2? Is that a possible solution for my original equation? No. So we're going to cross it out. We eliminate x equals 2. And then for the 5, I've got 3 plus the square root of 5 minus 1 is equal to 5. So what's 5 minus 1? 4. And what's the square root of 4? 2. And this one works. So the solution to the radical equation would be only x equals 5. So this x equals 2 that we got right here, we call this an extraneous root. It's explained more on the next page. The process used in that second example led to an answer which was not a root of the original equation. And I talked about that the other day. Yep. So that solution of x equals 2 in the previous question fits this equation down here, but does not actually fit the original equation, and that has to do with the squaring of the radical. Changes some parts of the equation. So it is important when you're solving these radical equations that you make sure that the solution is valid, that it fits the original equation. And the other thing that we would also want to do is make sure that in this case, the value of x, or this x minus 1, has to be greater than or equal to 0, because I can't take the square root of a negative number. So my x values also have to be greater than 1. So if I had solved this and I had gotten that x equaled negative 5, I would eliminate that right from the beginning. I wouldn't need to verify it, because it does not fit the restriction as well. So you have to consider the restrictions, and then you also have to verify the answer. So it is important to check our answers with these radical equations. So in general, the process of squaring may lead to an answer that does not satisfy the original equation. We call this an extraneous solution or an extraneous root. There's the flow chart for solving radical equations algebraically. You want to start off by isolating the radical term. If there are two radical terms, you isolate the more complex one, or you put one on one side and one on the other side, if that's possible. Square both sides of the equation, and in the squaring process, if you should still end up with a radical, and we will have an example of that, you would then repeat the process. So you would repeat the process of squaring both sides until you were able to fully eliminate the radical symbol from the equation. Then you'd go through the steps of solving like we have in the past, always checking that my solutions are verified. So if we look at class example number 3. If I quickly look at this x plus 3 tells me that my values have to be greater than or equal to negative 3. Anything smaller than negative 3 is going to make that side negative. On this side, if I let this equal 0, I put the 5 over and divide by 3, I have that x will have to be greater than 5/3. Well, it can't be greater than negative 3 and greater than 5/3. If I picture a number line, here's negative 3, here's 5/3. If it's bigger than this and bigger than that one, I can only use this solution. The negative 3 no longer has input because negative 2, which works here, would not work in this side. So what I need to make sure is that my solutions are going to be bigger than 5/3. So I can even erase this part. So now that I have my restriction, I have a radical on both sides of the equation. To get rid of the radical, I square. What I do to one side, I do to the other, so I square both sides of the equation. And I've got x plus 3 equals 3x minus 5. So the idea is to get the x's on one side so that I can isolate them. So do I want to move the 1x or the 3x? The 1. So if I subtract by 1x on each side, how many x's would I be left with? 2. And then I'm going to want to get rid of the negative 5. So how do I get rid of the negative 5? Add 5, so what's 3 plus 5? And then I divide by 2, and x would equal 4. Is 4 bigger than 5/3? Yes. So I fit the restriction, but now I need to double check it. So I have the square root of 4 plus 3 on one side, and then I have the square root of 3 times 4 minus 5 on the other side. So what's 4 plus 3? 4 times 3 minus 5. Are the two sides equal? So this is a valid solution to the radical. Okay? So if I look at this one here, I already know that x has to be greater than 5/3 for this solution. And this one would be that x has to be greater than or equal to positive 3. So of the two solutions, which one holds true for any possibility? The 5/3 or the 3? The 3. The 5/3 isn't going to work because if I put 5/3 into here, I end up with a negative. So my solution has to be bigger than 3. Now I can square both sides. X minus 3, 3x minus 5. Subtract by x, and I get 2 of them. Add 5, I get 2 of them. What does x equal? Is this a valid solution? Why not? It's not greater than 3. This is not valid. And I could check this. I could verify. 1 minus 3 is equal to what? Negative 2, which I cannot have. I cannot square root a negative number. Even if I checked the other side, 3 times 1 minus 5 also equals negative 2. The fact that the two sides equal each other has nothing to do with, oh, well, I verified it, it's okay. I can't square root a negative number.
All right, I'm doing math.
Because I can't square root a negative number, that solution's not valid. So we say that there is no solution. Graphically, if I graphed these two equations and said y1 and y2, I would get two equations that never intersected. That's what it would look like graphically. There would be no common point of intersection. Okay.
It's ready for that fire drill?
Okay, next question. I have two radicals on the same side of the equation. So if you remember that flow chart, it says isolate the harder radical. Which one looks to be the harder radical? The x minus 3. So to isolate the x minus 3, I move the root x to the other side. Now, this one here, valid solutions are anything greater than 0. What are my valid solutions for this one? Greater than 3. So it can't be greater than 0 and greater than 3. It just has to be greater than 3. So that gives me my valid solution range. Now that I have my harder radical isolated, I square both sides. When I square the left-hand side, my radical disappears. When I go to square the other side, I might find it easier to rewrite. It might be easier to put 5 minus root x twice, so that when I go to expand this side and use the distributive property, I get 25. I'm going to get a negative 5 root x, another negative 5 root x, and then when I multiply the last two terms, I get x times, or root x times root x, which would be just x. If I collect my like terms, I get negative 10 root x's. I still have a radical, which means I still am going to have to do a squaring process again to get rid of that radical. But before I square it, I have to isolate it. So I'm going to move the x and the 25 to the other side. If I move x to the other side, it cancels out the other x, so I'm left with 0. If I put the 25 to the other side, I get now I can square both sides of the equation. If I take negative 28 and I square it, what would I get? If I take negative 10 and square it, so now I have 100x. Divide by 100. What is 784 divided by 100? Okay, what is that as a fraction?
Oh, 196 over.
Is 7.84 greater than 3? Yeah, so it's going to hold that part valid. I do want to double check that when I put it into the equation, it makes the original equation true. So when I do that, I'm going to leave it in its fraction form. Or I guess I could put it as a decimal. It's a terminating decimal, so that'll be fine. What's the square root of 7.84? And I've got 4.84. What's the square root of 4.84? And 2.8 plus 2.2 is 5. So the two sides equal each other, so this becomes a valid solution. So I think yesterday I gave you question number 4, right? B and C?
Yeah.
So question 5, A and D, 7 and 8A, and 9, 10, 11.